So we're still working in section 8.3, so this is still dealing with solubility. Section 8.3. So now what we're going to talk about in this video is to talk about our solubility rules. Oops. So if we call from our previous lecture, okay, our solubility depends on a number of things. Basically, we're looking at, we talked about temperature. We're not going to discuss the presence of other solutes or contaminants. Our type of solvent, we're going to be dealing with water now, so that doesn't change. So basically our type of solute and looking at our solute-solvent interaction is going to depend on these solubility rules. Okay, and again, I put these kind of in quotations because they really are more like guidelines. Okay, they aren't always true, but it gives us something to start with. It gives us something to grasp onto rather than just having to memorize, hundreds of different solubilities. Okay, it gives us some of the general concepts. So what happens with this solubility of the solubility of compounds in water is there is no rhyme or reason or explanation or trends as to why one compound is soluble than the other. Okay, and please don't try and rationalize this. Okay, these solubility rules have been developed for a reason, and it's because there really is no rhyme or reason. So, if you really want to, yes, go ahead and dive into it. Try and make some sort of trend and rationalization to it. But trust me, chemists have been looking at that for years, and they have not come up with anything. Okay, for every trend that they develop, there are just too many exceptions to make the trend even worthwhile knowing. Okay, so we just kind of have these general rules, or kind of, I call them guidelines. Okay. All right, so we're going to use these rules, okay, in two different ways. So 2 ways to use our rules. The first way is we're going to just determine if a compound is soluble or insoluble. The second way, okay, is kind of we're still going to use this concept, but we're going to actually determine whether or not a solid is going to form if we combine two different chemicals, two different solutions. So if basically what we're going to do is, to do this, we're going to have to determine, determine the formulas of our products. And basically what products are we looking at? And then we're going to determine their phases. Okay, or states. And that's where basically we're determining if the compound is soluble or insoluble. Okay. If a compound is soluble, that means that it's going to dissolve in water. And if we recall from chapter 6, anytime that we have something dissolved in water, that phase or that state is called aqueous. If it is insoluble, okay, that means that it's going to form a precipitate. And this precipitate here, we can shorthand PPT. Sometimes that's the phase that will be shown. But when we write this in a chemical equation, that precipitate, what it means is it is going to form something that is solid. Okay. So we're looking at something in the gas phase. On occasion, you may form bubbles. So this is or. So you could form a precipitate, or you could form bubbles. Basically, bubbles mean that you're forming a gas. And most of the time, you're going to look at a precipitate. When a precipitate forms, what happens is the solutions go from clear, okay, not colorless, but clear. They can still have a color to them. Clear meaning you can see through them. So Kool-Aid is a clear liquid. Water is a clear liquid. We would classify water as clear and colorless. Very distinct. It's not just clear. And so when we mix two clear solutions together, if it turns cloudy, that means that we have a precipitate there, or we have something that's solid that's formed. Okay, milk is an example of a solution that has a precipitate in it. Okay, it's very cloudy. That precipitate are the fat molecules in there, and those fat molecules are actually in the solid phase. Okay, yes, they're distributed throughout, so they're really, really, really small solid particles, but they are in there. Okay, if you've ever had raw milk, or if you've had milk that's not homogenized, okay, homogeneous versus heterogeneous mixture, your cream or your fats separate from the liquid portion or the water portion, and you have to shake it up in order to get those mixed back in. Okay, what you're dealing with is you have an insoluble fat that likes to separate out. So these are the two ways that we can use the rules. Okay. So first, let's just practice determining if a compound is soluble or insoluble. And then I'll show you an example of determining whether a solid will form when two solutions are combined. Okay. So first off, we need to actually discuss what these rules are. Okay. Your book gives you some solubility rules. In the paperback version, it's on page 311, table 8. And these are solubility rules for ionic solids in water. And this is actually, it's a very, very, very simplistic table. I actually don't like it because it's too simplistic. It doesn't have enough information on there. I mean, it seems like it has a lot on there, but it is not complete, and we're going to be dealing with a lot of different compounds. So this solubility table gets you so far. Okay, it's a basic one. It'll get you started in the right direction. But we want to use one that's a little more intricate. So on Moodle in the Chapter 8 section, you'll find a link to an image of the solubility rules that I suggest you use. Okay. You can use whichever solubility table or rules that you like. But the link that I will provide on the Moodle site will be the solubility rules that will be available on the exam. So on that on the final exam, the cumulative one. Okay, so you don't have to memorize these rules. They will be given to you. And I would suggest getting used to the solubility rules that are posted on Moodle so that you aren't surprised when you get to the exam for that. So let's work through some examples. So we have K2S, which is potassium sulfide. We have calcium sulfate, and this is lead 2 sulfide. Okay, remember, lead is one of our transition metals, so it has to have that Roman numeral in its name. Okay, so lead 2 sulfide. If we look at the solubility rules of these, let's start with K2S. We want to look at how these are made up, okay, and what ions we're looking at. So we basically have K plus, and we have the sulfide ion, S2 minus. And if we look up our solubility rules, we'll notice that anything that is combined with potassium ion is going to be soluble. Okay, and although I said you don't have to memorize any of this, that is one that's worth memorizing. So knowing that anything that contains potassium ion, that's going to be soluble. So it's soluble. Other ones that are worth memorizing, I'll put these up here. Basically K plus, Na plus, and nitrate ions, so NO3 minus. Anytime these are paired with anything, these are always soluble. This is worth knowing. I don't really like the word memorization. Basically, those are 3 that are worth putting into your memory banks. They're the most common ions. So usually if you can rule these out, it makes your life much simpler when determining if things are soluble or not. All right. Our next one here, we have calcium sulfate. So this is made up of calcium 2+, and we have our sulfate ion. We'll find calcium 2+ actually isn't on the solubility rules. We need to look it up by its anion, the sulfate anion. And we'll see that all sulfates are soluble except for when they contain certain metals like calcium. So if this were combined with, say, potassium, it would be soluble, but since it has this calcium here, this means that our calcium sulfate is insoluble. All right. Go ahead and try out your lead 2 sulfate. Try that out on your own. And pause the video and the solution will be ready when you are. All right. So for our solubility here, we have Pb2+, and we have our sulfide ions, excuse me. So lead 2+ isn't on our solubility rules. Okay, so we have to look up the sulfide ion, and we'll see there that only alkali metals and ammonium ions, the NH4+, sulfides are soluble. Okay. So the only way for this to be soluble, it's obviously not NH4+. Hopefully that is obvious to you. But the only way that this is going to be soluble is if Pb2+ is an alkali metal. Okay, so remember that stems back from chapter 3. All of your alkali metals are in group 1A. Lead 2+ is not in 1A. It's a transition metal. So lead 2 sulfide, this PbS, is going to be insoluble. So that is just an example of working through our solubility rules to determine if our compound is soluble or insoluble. Now what I want to do is go through an example of determining whether a solid will form when two solutions are combined. Okay, so our second way of using our solubility rules. So the two solutions that we want to look at, basically we're going to predict whether a solid is going to form between lead 2 nitrate and potassium chloride. So basically what we're looking at is we have this PbNO3 and remember anything that's with the nitrate ion is soluble, so this is in the aqueous phase. We're going to combine that with potassium chloride. Anything with potassium is going to be soluble, so it's in the aqueous phase. And what we want to do is try and determine our products here. Okay, once we determine our products, then we can use our solubility rules to determine if they're soluble or insoluble. So we have to figure out what our products are. How we do that is we have to be able to identify what this type of reaction is. Okay, and how we do that, that stems back from chapter 6, I believe section 6.2, which we skipped, but we're going to now start covering it in this section, and we'll also cover it for your lab for chapter 8. Okay. This type of reaction is called a double displacement reaction. Some other names that this might go by, an ionic reaction. Or sometimes instead of displacement, they call it a replacement. So it could be a double replacement reaction. The general kind of pathway or layout of what's going to happen is these are two ionic compounds, a metal with a nonmetal, metal with a nonmetal. And we can kind of look at them in terms of we have compound A, B. So A is our metal, B is our nonmetal. And here's where identifying your polyatomics is important, and that we are going to treat B as NO3, okay, that entire polyatomic ion. So we're going to have AB plus CD. Okay, so C is our second metal in our second compound, and D is our anion, okay, our non-metal in the second compound. And basically, all that's going to happen is our ions are going to swap partners. Okay, remember, ionic compounds like to be combined with a positive and a minus, okay, plus and a positive and a negative. So our positives and negatives are basically going to swap partners. Okay. So we have our positive from our first one is A, and we're going to combine that. We're going to swap partners, so he's going to combine with the negative from our second one. So I'll have AD, and our other compound is going to be the result of the other pairing. Okay, and we always list our metal first, so we're going to take our C, and that's going to combine with the B. So basically what we want to do is we have to figure out how A and B are going to combine, following our rules from chapter 5, and how C and B are going to combine. So we're kind of going to, let's go through this step by step. So let's look at step 1. Step 1, we want to split apart our ions, okay, and determine their charges. So in our case, we're going to split apart our PB and our nitrate. So we have PB, and we have NO3, okay, and we want to determine their charges. So we have to memorize or know that nitrate has a -1 charge. Okay, that's stemming from chapter 5, talking about the polyatomic ions. And you need to know those that were listed on your pre-lecture worksheet. You need to have those memorized. Okay, or you can also consult the solubility rules. It probably has the formulas and charges there. We had 2 of our nitrates in our formula with only 1 lead, so that means our lead has to have a 2+ charge on it. And then we're going to split apart our potassium and our chloride ions. And consulting a periodic table, we know that potassium is in group 1A, so it forms a +1 charge. Chloride ion is in group 7A. It's one of the halogens, so it has a -1 charge. So step 2, once we have our ions, okay, now we're going to combine our ions, swapping our partners, and we have to make sure that we balance our charges so that our formula is charge neutral. Okay, so following the rules, there's nothing new here. We're just following the rules from chapter 5. The easiest way to do this is your cross-charge method. So we have Pb2+ is going to combine with Cl-, and our K+ is going to combine with the NO3-. So our 2 goes down to the chlorine, our 1 goes down to the lead. So our formula, we have PbCl2. Over here, same thing, our cross charge. The 1 from potassium goes to the outside of the NO3. The 1 from NO3 goes to the subscript for potassium. So we have 1 of each of KNO3. Step 3 is to look at our solubility rules and determine what our phases are going to be. So our PbCl2, and we have lead 2+, and we have our chloride ion. Lead won't be found on there, but chloride is. And our solubility rules say that all chlorides, bromides, and iodides are soluble, except for those of silver ion, mercury ion, and lead 2+. Okay. So they're soluble except for with lead. Lead is there. That means that PbCl2 is insoluble, which anything that is insoluble is going to form a precipitate, which has a phase of solid. So we're going to have PbCl2 as a solid. Last one here, potassium nitrate. Has potassium ion in it and nitrate ion in it. So if we look back up to the ones that I said are worth knowing, okay, potassium's there, nitrate's there, always soluble, which means that KNO3 must be soluble. And if something is soluble, that means it's going to dissolve in water, so it's going to be aqueous. And again, this is solid because this is insoluble. KNO3 is soluble, and that's why it is aqueous. Now, we've answered this question because we're looking to predict whether a solid will form, and this is our solid, so yes, a solid will form. A lot of times the final step of what I would ask, say, on an exam question is what is the balanced chemical equation. Okay, so you'd have to write out then your products. Well, let's go ahead and do that. That's a good practice for us. So let me work on, let's look at this. Let's kind of call this an asterisk step 4. Not really asked for in the question, but definitely worth us looking at, as we want to write a complete balanced chemical equation. So we have PbNO3. That started out as aqueous. So did our KCl. And we know we're forming our PbCl2. We know that's a solid. And KNO3, aqueous. So, to balance it, remember we pick one compound to start out with, and we'll assign it a 1. Okay, I'm going to start with our lead 2 nitrate, okay, our PbNO3 because as those parentheses, it looks a little scary to me. We have 1 lead, so I go over to my products. I need a 1 out in front of the PbCl2. Go back to my starting compound. Now I have nitrate here, and I have nitrate over in the products. So rather than balancing the nitrogen and the oxygen separately, okay, I can consider them together because they stay together. So I'm actually going to balance the nitrate ions, and I have 2 nitrates. So over in my potassium nitrate, I only have 1 right now. So if I put a 2 out in front as my coefficient, I will have 2 nitrates. Then my last thing to balance is my potassium and my chlorine here. I have 2 potassiums for my potassium nitrate. So I put a 2 out in front, and that balances out. I have 2 chlorines then, and 2 chlorines. So that is our final balanced chemical equation for this double displacement reaction.